All right, there's that. Now that all that's been settled, let's get on to our main presentation for this evening. So we have John, and correct me if I got this wrong, W6NBC. We got, as Harry mentioned, some interesting talk about antennas, copper tape, and all that. So John, feel free to take it away.
Thank you for having me. I enjoy making these presentations to radio clubs. Zoom and COVID came along at a remarkably the same time, and which I'm very not happy with COVID, but I'm happy with Zoom and the other methods. There are several other good ones too. Tonight we're going to talk about an antenna that I've had a great deal of fun with and has now morphed itself into several other versions of the same antenna. I'll show you a couple of them here tonight, which haven't been made public, using self-adhesive copper and aluminum tape, basically put on some kind of tubing, usually PVC, but I've put it on cardboard tubes too, to make a helix, a shortened dipole, basically. That's what we're going to see tonight. Very functional little antenna, particularly if you want to make something lightweight and portable, but they're also pretty good for also making small antennas. This whole concept started some time ago at my weekly ham breakfast, which incidentally is beginning to meet again at the local restaurant. These are all the local hams and many of them around my area here on the central coast of California. And we were discussing the kind of articles that QST likes. They like nice, simple construction ones. So I said, okay, let's make up the simplest one you can think of. And so we cogitated about that over breakfast. And we decided if you're going to make a simple antenna, absolutely has to be made out of one of two or maybe both of two things: PVC pipe or copper pipe. Hams love these materials. As you can see there on the right is the famous copper pipe 2-meter J-pole, which probably more of those have been made than anything else in homebrew antennas. So on my way home from breakfast, I thought about what would be took the ideas from breakfast, and in 2 hours I had it built, 2 to 3 hours. Sat down, wrote the article about it, emailed it off that very morning to QST editor, who knows me pretty well because I've written 23 articles now for QST. And in a week they had accepted it, and in 3 months they had it published. This is my all-time record with QST. Usually it's more like a year. Okay, this was the actual article as it appeared in QST in October 2020. It's had a lot of reader response. Quite a number of them have been built around the world, actually. I've had New Zealand and Australia and India and Spain and Italy, and certainly the UK has responded. This particular antenna was made of 1-inch self-adhesive copper tape, which I obtained on Amazon. You can get it in 1/4 inch, 1/2 inch, 3/4, whatever you like. This is 1 inch. I used it for this particular antenna, which you see there on the right. 1.5 mil copper, 1 inch wide. You get 45 feet here for $12 or something like that. However, you can also find it down at your local garden center. It's often called snail tape down there. You see that planter at the bottom. You put a strip of it around your planters, and the snails don't seem to like to crawl over copper. I guess their wet foot makes half of a battery, and it must shock them or something. But you can get it there too, but Amazon's probably the best place to get it. All right, how does this particular little antenna work? What are some of the principles behind it? There are some good antenna design principles here. Well, all of you, I'm sure, understand what a loading coil is. Probably many of you have mobile HF antennas. That one on the left there is an MFJ mobile on a screwdriver, MFJ, I think. And the one in the middle there is just a little loading coil in a wire dipole made with winding some copper wire onto a piece of PVC. Common. We know what loading coils for. Their object is to shorten an antenna. or to make an antenna that's less than half a wavelength long look like it is a half wavelength long to the transmitter. Well, as many of us may know, loading coils come in two different forms. You can either find them as a discrete loading coil. That's what we saw in the last slide there, were two discrete loading coils where the turns are close together and in one small space. But most of the antenna is still wire or aluminum conductor. But there's no reason you have to do it that way. You can also do it by stretching that loading coil out so that it makes up the whole antenna. And it's called continuous loading. And you'll see these in various mobile whip antennas. You'll often see continuous loading used there. CB antennas often used it. However, one must be really careful when you're designing a small antenna because of the efficiency of a small antenna. A lot of hams don't like to talk about efficiency. I have a good buddy. His call sign is N6ND. We call him No Donuts. He totally dislikes me to talk about efficiency because he likes making antennas out of anything he can make them out of. And he makes contacts regardless whether they're efficient or not. Well, but it's an important feature in designing an antenna, efficiency. That's because of a factor, two types of resistances that are found in all antennas. Here's the circuit diagram of all antennas. An antenna is virtually made up of some kind of coil or inductance. It's distributed inductance, but it's real inductance. And it also has some distributed capacity, which you see on the right. But all antennas also have two resistances in them. R sub C, or ohmic resistance. That's just the number of ohms in the actual conductor, kind of ohms that you read with an ohm meter. But there's another resistance, and this is the important resistance. This is what makes the antenna work. It's called radiation resistance, and it's in series with the ohmic resistance. And as you'll notice in this circuit, the power that comes from that transmitter, that little squiggly circle at the bottom, is tuned by the coil and the capacitor, but it has to pass through the ohmic resistance and the radiation resistance. So each of those share a portion of the power. Ideally, we want the radiation resistance to be high and the ohmic resistance to be low if we want an efficient antenna. So efficiency is a ratio between conductor resistance and radiation resistance. Okay, but what is radiation resistance? That's a kind of a mystery. Okay, here's the metaphor I like. It's a kind of a funny little metaphor, but I like it. I think it's a good one. Here's a bowl of Jell-O, or as the Brits like to call it, a bowl of jelly. I like to visualize an antenna and the space that surrounds it, like the antenna is buried in this gigantic bowl of Jell-O, the size of the universe. No, we're not returning to the theories of the 19th century about the luminiferous ether. This is the way it works, not what it literally is, but it does work this way. An antenna has to have some place for the power to go. If it wasn't for the radiation resistance, all that your transmitter would make would be heat. But because the antenna is loaded by space, that infinite bowl of Jell-O that surrounds it's RF Jell-O that surrounds that antenna, there's now a place for the RF in your antenna to go. And when you put RF or alternating current into that antenna, in that bowl, that RF current shakes that Jell-O or vibrates it or distorts it and causes a radio wave to appear. This is what James Clerk Maxwell proved with his equations back in the middle of the 19th century. But that resistance must be there. Otherwise, the antenna would deliver no power to space, but it has to share its presence, has to share the transmitter power with the conductor resistance. Okay, therefore, it's very important in all antennas, usually not a big worry in a full-size antenna, but in small antennas, it becomes very important to keep the conductor resistance low compared to that radiation resistance. And as I say here, this is very acute in small antennas, so its efficiency is a ratio of the two. That's why in the design I'm going to show you today, and in all these tape antennas, you want to use wide copper tape, not thin, narrow tape. You can use it, but you're going to compromise the antenna if you do. And also, it's a good idea to widely space the turns. A lot of hams don't know this, and when they wind loading coils, put the turns right next to each other. Not good, because when you put the turns next to each other, skin effect of the adjacent turn removes some of that conductor and increases the inefficiency or decreases the efficiency. Spacing of the copper tape should be at least 1-to-1. It's okay at 1-to-1. There's a little bit of adjacent turn skin effect loss with turn space 1-to-1. That's 1 times the diameter of the conductor. If you get your turn space 3-to-1, where there's 3 times the ratio, where the spacing of the turns is 3 times the diameter of the conductor, you have very little adjacent turn skin effect loss. I chose 1-to-1 because it's a reasonable compromise. It saves making the antenna too long. Okay, you might ask yourselves, how does this little antenna we're going to show you today, which by the way is a full 2-meter antenna, the one I'm showing you, and I've got some others that are 6 meters and otherwise. This little 18-inch antenna is highly efficient, has the radiation as the gain of a J-pole, and yet is only 18 inches long. How does it compare in performance to a full-size J-pole? Okay, here's the proof of the pudding. Here's the radiation pattern of this little antenna looked at from the side. As you can see, it's the classic donut-shaped pattern that we're all familiar with a dipole in elevation, or that is looking at it from the side. Has a gain of about 2.1 dBi, or 1.6 dBi, I'm sorry. And this is the one at the right is looking down at it from the top. It's omnidirectional, and the maximum gain is 1.6 dBi. Here, by the way, is its bandwidth. Also, the wide tape is important for good bandwidth. As you can see, this antenna has fine bandwidth. This is more than the whole 2-meter band here, and it has good SWR across the whole 2-meter band and beyond. Okay, comparing this now to your famous copper pipe J-pole, and I did this in EasyNet, so I know it's quite reliable. This little antenna has a maximum gain towards the horizon of 1.6 dBi, whereas a J-pole, which is really just a dipole, the bottom section of a J-pole does not radiate. Just the top section does. It's a half-wave dipole on top of a J-pole, has a gain of 2.1. So we're only down by half a dB. Pretty small for an antenna that's only 18 inches tall. Now I ask you, which one of these antenna on your roof is your neighbor going to notice, or more than that, your HOA? Which one of these antennas is it going to notice? Well, it's certainly going to see the 5-foot J-pole, but it may not see that 18-inch one that we're going to build here. All right, let's look at the construction. I'll give you some preliminaries, then I'll actually build one for you. I did a little video of myself building one, which we'll look at. Putting on copper tape onto something is like putting down self-adhesive shelf paper, if you've ever tried to do that. It's not easy to do. So to get it onto this piece of plastic PVC, you're going to need to make up a little guide strip so that you can make a helical mark on that piece of PVC. You want to put 10 turns of it to start with on a piece of 1.25 inch PVC pipe. And to make the mark on there, you need to cut yourself a little flexible plastic strip, or you can use heavy paper, just cardstock, and make it 2 inches wide so that you can wrap it around and butt the edges together and then slowly unwrap it and make a mark on the tubings to show you where this helix goes. 10 turns. You'll also need to make up for yourself a little pigtail. This is just a piece of our G58 or Mini 8, I think it's Mini 8 in this case, and with some heat shrink tubing on it for weatherproofing, and a couple of number 6 ring terminals at the end, with this one end of it fanned out so that the 2 conductors of the coax for about 3 inches are fanned out into 2 separate conductors to hook up to the copper tape ends. Mini 8, 58 are both good. Make up a short pigtail, 6 to 8 feet long is fine. Any more, I'd adapt up to bigger coax to get into the shack. All right, we need to tune this antenna up. And this is how I did it and how you will do it. It's very simple, straightforward. Here's the antenna when it was finely tuned. You'll notice that it does not have 10 turns on it. It has only 7 turns here in it, or 8 turns in its final configuration. And why is that? Why did that happen? Well, if you take any dipole and look at the center, if it's a full-size dipole, it's going to have an impedance of about 25 ohms. 75 or 72 ohms in the middle in free space. A shortened antenna is going to be less. So if the original 10 turns that we put on this antenna would have had an impedance of about 25 ohms in the center, we've got to get that higher. That won't match the coax very well. But here's an important trick. If you simply move off center on any small antenna, get away from the center of the antenna, the impedance rises. Why? Well, between the middle of low impedance and the end of high impedance, somewhere in there is 50 ohms. And all I had to do was take tape off the ends, more off the top than off the bottom, and voila, I found one of the 50 ohm points. In fact, there are 2 of them, one above and one below the center of this antenna. We'll see this happening. It's easy to tune this antenna. Okay, the first thing you do, and here's the antenna with the full 10 wraps of tape and the feed point to start with in the middle. The first thing you do is to start whacking turns off the top of this antenna. Starts with 5 turns on top and 5 turns on the bottom. And when you start, the SWR will be bad, and the frequency will not be in the middle of the 2-meter band. It'll be low, about 118 megahertz, actually. If I measured this when it still had 10 turns on it. First thing you do is to start taking turns by removing a small amount at a time from the top. And the first thing you do is to pay attention to the SWR. Don't pay any attention when you tune up any new antenna. Don't pay any attention to where it's tuned. That's the second step of tuning up any antenna. The first step is to get the SWR right. And that's what I did. I started whacking turns off the top until I got it down, and I found the match point. It was matched at 118 megahertz. Then I did the tuning. The reason you do it in this order is simple. The SWR will not move very much when you tune the length of a dipole. So if you put up a dipole and it's a shortened dipole, and you try to find this 50 ohm point, and you tune it until you whack ends off one end of it until you find the 50 ohm point, and then you take stuff off of both ends. You won't change the SWR very much at all. It'll stay pretty close, and you can just do a fine tune at the end.
Let's look at how to build one of these antennas. Here's a finished model. It begins with a 30-inch minimum piece of 1.25-inch PVC tubing. Other sizes can be used, but that's what this one is built from. You can also make it longer if you wish, and include the mast for the antenna as well. First thing you're going to need to do is to make a mark, a long spiral mark on this piece of tubing to guide you in applying the self-adhesive tape. Self-adhesive materials, as many of us know, are difficult to apply. I use this little appliance that I made for myself. It's a 5 feet long piece of plastic, flexible plastic, cut from the covers of a 8.5 by 11 notebook or from notebook dividers. And it's taped together straight to make a single piece. This piece of plastic then, you wind beginning at the top end of the tube, tape it on, and then wind it onto the tube helically so that the ends of this stuck together. Keeping the edges of the plastic strip butted together, wind the complete strip onto the tubing. When you are finished, begin at the loose end and with a felt tip marking pen here, a Sharpie in this case, begin marking along the edge of that pipe to create a helical guide mark on the tube. This is to help you know where to put the copper tape. This is what the tube will look like after you have it completely marked. From the top end on the left here, the end of it down here. It's a 30-inch tube again, can be longer. Now, with the copper tape, peel back a little bit of the backing and begin taping this tape onto the PVC pipe using the guide mark that you have marked on the tape. Pull back the backing slowly as you wind it on. If you make little wrinkles or even if you break the tape, you can patch it by using a 1-inch overlap piece. Copper is very malleable and any wrinkles in it can be smoothed out easily afterwards. So wind the copper onto the tubing, the whole length, 10 turns, keeping it aligned with the mark that you made on the tubing earlier.
1.25 inch pipe.
Here I've got a little bit of a wrinkle, so I'm just moving the tape over a little. This wrinkle won't matter. This is what you will have when you are finished. 10 wraps of the 1-inch copper tape, accurately spaced 1 inches apart on the tubing. 10 wraps are necessary so that the initial tune-up frequency will be low, so that you can adjust the tuning of this antenna by removing copper tape. You can add copper tape too, but you'll need to make a little patch across the gap. If you intend to make this antenna for another band, begin with a total length of about 80% of the half wavelength, or about 40 inches is what I used on 2 meters. Use the same tape diameter, same tape width, and space it the same distance apart. Just make the pipe bigger and the total pipe longer. And you should be able to put it on pretty much any band you wish, within size limitations. The next thing you need to do is to go to the halfway mark on the antenna at 5 turns, remove 1 inch of the copper tape, and then drill a 3/4 inch hole. You can see the 3/4 inch hole here. I used a common hand drill and a step drill, which is a convenient tool for making holes in sheet metal and plastic tubing and plastic sheet or tubing. The coax comes up from the bottom of the antenna through the tube and connects to two holes that are drilled and tapped into the edge of the copper tape. You can also use sheet metal screws. These are 632 machine screws in holes that have been drilled and tapped. The coax that comes up, the pigtail, has ring terminals on the end of it, and the end is fanned out so that the two conductors, the braid and the outer, are separate wires. The other end of the pigtail, which is 8 feet long, has a connector on it. The next step is to make a balun. It is my contention that all antennas need a balun. I typically use 1-to-1 choke balance on every antenna that I make. I certainly use them for testing to avoid reactions to the coax. This balun is a simple item. Simply take the coax and wind 4 to 6 turns of the coax, in this case mini 8X, on a piece of 1/2-inch pipe. And then simply take it and shove it up into the tube. It's really quite simple to do. Then I made this small device, a little disc which I cut out of a food container. And here's a typical coupling that's used for 1.25-inch pipe. I put this little spacer over the coax below the tubing right there, and it keeps it inside of the spacer. Here is the final chore, tuning and matching the antenna. With the antenna mounted free of other objects, not as you see it here, I just have it here for the picture. You will begin by removing tape because the antenna is too long, so it is low in frequency and the SWR is not good. The first chore is to get the SWR low. You do this by removing tape from the top, which causes the feed point to move off center from a low impedance point until it finds a 50 ohm point. Once you find the good SWR, then start removing tape both from the top and the bottom in small increments, 1/2 inch at a time, same. And eventually you'll be able to walk this antenna right onto frequency. Here you see the frequency sweep of this antenna with 10 turns. As expected, the frequency is low and the SWR moderately high. The final touches for this antenna are to put a cap on the top end and to cover the feed point with some self-vulcanizing tape. You can use ordinary electrical tape if you want. I prefer this self-vulcanizing stuff. You can leave the copper as you wish. It will only become darker with age. Or if you like, you can paint the whole antenna. Or even if you wish, you can put the whole thing in heat shrink tubing. In any case, it's a very handy little antenna for several purposes. First of all, it has the gain roughly of a J-pole. It's a dipole, just like the J-pole is. The only difference is its bandwidth is narrower. But it's certainly perfectly adequate for the 2-meter band because of the wide copper conductors. It's a good antenna to be used for example, a bike-a-thon, where you need a portable antenna, let's say for the base station. Or you can carry it with you if you like, if you're at an event, and use it connected to a handheld to extend the range. It's a good little performer, and quite a number of them have been built, and it has brought in a lot of interest from readers. My main interest now is to see if it can be taken to other bands. If you want to try to make it for another band, it's straightforward. Just scale it inversely to frequency, put it on larger pipe, use the same copper tape, and make it a larger diameter. But I think it's possible to take this design down to lower frequencies, if you would, certainly to 6 meters. So try out this little gem. I think you'll like it.
Okay. I've added this section since doing that little piece of video because I have tried out other bands. And we're going to take a look at what some of the things that have come since that previous material was recorded. I lived over in the UK for quite a number of years. I'm still M0GCK, by the way, and so I gave this lecture to a radio club over there, and its president, G4HHC, was very interested, and he decided to build one of them. But he decided to build one for 4 meters. 4 meters is a band we don't have yet here in the U.S. Model airplane radio control has been there for years, although most of that's moving up into the low gigahertz range now. And here's his 4 meter version of this antenna. It's about 3 inches, 3.5 inches in diameter, and he made it with 2-inch wide tape. No, it's still 1-inch tape. And he has a 3D printer, as do I. I love my 3D printer. And he printed these little snap together sections. Here he uses, looks like 1, 2, 3, 4, 5, 6 sections of 3D printed stuff that just sort of slip together to make the tubing, which I thought was a very clever idea. And he molded or 3D molded in some bosses to hold the coax in the center of the pipe, which is a good idea. So it doesn't detune the helix. Now, here's one that I've been working on recently. This is my new one. I've submitted this article to QST. It hasn't been published yet or even accepted yet, just barely went in a couple of days ago. And here you see Snoopy sitting on top of, well, in this case, a birdhouse. And of course, there's Woodstock. That's Woodstock's birdhouse. This is a little 3D printed project I had lots of fun doing. And the nice thing about this is it's very, very stealthy. There's the whole antenna on the right. And you can see the pole is not round PVC, but it's a piece of plastic PVC rain gutter. You can buy this in 8-foot lengths from your local build-it store quite inexpensively. Very lightweight, makes a nice support to hold up the little birdhouse. I show it here before I painted it. I left it; it's unpainted in this picture, just so we could show it. But if you want to paint it with white paint, then nobody'd even notice the aluminum tape. This one's built with aluminum tape, which is almost as good as copper. And aluminum tape is easier to get. You often find it at dollar stores and so forth. If you look near the bottom, down near the bottom, I think I can bring my cursor down there. You can see the feed point down here. It's quite a bit off center in this particular antenna. And I decided to do it. You can use either the upper or the lower 50 ohm point. There's one up here and there's one down here. It's just made for shorter coax up to it. The balun is inside of the tube, or you can put it outside. And this one is very neighbor friendly. Nobody has any idea that this cute little birdhouse is hatching some chicks on top of a highly efficient 6-meter antenna. Here's the actual performance characteristics of this 6-meter version. And as you can see, it's tuned there a little below 52, about 51 megahertz, and it has an SWR across the entire 6-meter band of under 1.5 to 1. And it has the same 1.6 dBi gain, which is only half a dB less than a J-pole. So I ask you again, which one of these is your neighbor going to notice? A 13-foot tall copper J-pole on 6 meters, or this little neatly disguised little Snoopy tenna, or birdie tenna, as I sometimes call it. Here's the feed point for this particular one. I decided that pop rivets were the best way to attach it, although sheet metal screws work fine too. And there's the coax coming up from the bottom through the piece of rain gutter. And here's the marking of the rain gutter. I had to make some 4-inch wide guide strip, again out of the covers of some notebook dividers, and I drew the guideline along the rain gutter. Now let's consider this for other HF bands, because I got a lot of email. Oh, can I make this for other HF bands? Yes, of course you can, within limits, of course. I don't think this is too practical on 160, but it's certainly practical on maybe down to about 20 meters. The variables that you want to use if you want to move this antenna down onto HF are these four: the height of the pole, the width of the tape, the spacing between the turns of the tape, and the diameter of the pole. You can play with all of these factors to allow yourself to get more tape on it. I have a piece of 4-inch PVC that's 10 feet tall that has a nice 15-meter version on it, and it uses a 2-inch wide aluminum tape, just like the 6-meter version does. These are your variables. Now I have the top one, pole height, in red for a reason. If you don't care what the pole looks like, or if you're putting it someplace where the neighbors don't see it, or you don't have neighbors or HOA, then you can make the pole height anything you want. But I figured for the 6-meter one, or for trying to make the Snoopy tenna or the birdie tenna one on a lower band, you got to watch that you don't go too high, because I don't think a birdhouse 15 feet in the air would look quite right. I think neighbors might suspect there was something funny, but you certainly can change the tape width, and you certainly can change the tape spacing, and you certainly can change the pole diameter. These are all variables that will allow you to get lower in frequency if you want to. Again, remember though, we're going to fight against radiation resistance. And this is important to keep this in mind as you try to take this down to lower frequency. If you make the tape too narrow, or if you put them to the tape too close together, you're going to start compromising this antenna. So be cautious. You can go down, and a certain amount of compromise would be fine. But keep in mind the efficiency of the antenna as you go down. Because remember, and this is a truism for ham radio, not all radio contacts are made on efficient antennas. My good friend N6ND reminds me of this almost every breakfast meeting, that his funny wire antennas and coat hangers and other things are what still make good contacts. I mean, if you don't believe an inefficient antenna, which this one might be if you take it down too far, will make a contact, consider that radio on the left. Anybody ever made a successful contact on a rubber ducky? Well, of course you have. And that's a very inefficient antenna. Believe me, terribly inefficient. And lastly here, because that's all I want to say about this project. And lastly, let's do a shameless commercial here. As they say on radio and television, let's now pause for these important messages. Well, here's a little ad for my book on slot antennas for ham radio. And there's my little doggie, Lolly. No, her call sign is not D0GGY. Scan the little QR code and you'll get my contact information. And there it is, jportune@aol.com, or contact me through my website, W6NBC.com. And there we go, copper and aluminum tape helical antennas.
All right. Well, thank you so much, John. This has been great. This is a really, really cool presentation. I think it seems everybody enjoyed it as well, so I'm glad to see that. So thank you so much for this, and thank you for taking the time. At this point, it's about 9 o'clock, so our official meeting is closed. But John, you're welcome to stick around still if you like. I'm sure a few people might want to still talk to you, but other than that,
sure, I'll hang around for a while.
Cool.